Hello everyone, it is a audio recorded lecture on the topic aryl halides. Aryl halides are the compound that contain halogen atom directly attached to the benzene ring. They have general formula ARX. Any halogen compound that contains a benzene ring is not classified as aryl halide. Example, benzyl chloride is not an aryl halide because it is a substituted alkyl halide. Preparations: by direct halogenation, in presence of a halogen carrier such as Fe, chlorine or bromine readily replaces nuclear halogen of aromatic hydrocarbons. Mono, di and trichloro or bromo derivatives are obtained depending upon the proportion of halogen to hydrocarbon. Ortho and para-dichloro dibromobenzene are formed on further halogenation. Similarly, toluene on chlorination give ortho and para-chlorotoluenes. Second, nuclear halogenation of highly activated compounds like amines and phenols do not require any Lewis acid catalyst. Third, strongly deactivated aromatic compound require high temperature for the reaction. Fourth, halogen in presence of silver sulfate. This is very reactive halogenating agent for strongly deactivated compounds. Fifth, decomposition of disonium salt. When aqueous benzene disonium chloride is warmed at about 60 degrees Celsius with cuprous chloride in HCl, chlorobenzene is formed. This reaction is known as Sandmeyer's reaction. Sixth, reaction of PCl5 on phenols. Seventh, action of HOBr negative. Properties of aryl halides. First, aryl halides are heavier than water. Among the halides, the melting point and boiling point follows the order. Aryl iodides are the heaviest, then bromide, then chloride and then fluoride in melting point. Second, among the isomeric halides ortho, meta and para, the difference in their melting point are much wider than those in their boiling points. The melting point of ortho, meta, para dichlorobenzenes, for example, are 17 degree, minus 25 degree and minus 55 degree Celsius respectively, whereas their boiling points are 180 degree, 174 degree and 175 degree Celsius respectively. The para-isomer usually has the highest melting point, presumably due to its more symmetrical structure. Third, reaction involving halogen atom. A. Aromatic nucleophilic addition substitution reactions. Because of resonance, the halogen do not have a tendency to ionize in aryl halides. Thus, aryl halides normally do not undergo SN1 or SN2 type of reactions. For example, phenyl halide do not normally react with the nucleophiles such as OH, CN, etc. Such reactions takes place when halogen is activated under drastic conditions. For example, electron withdrawing group, nitrocyanide, sulfonic, carboxylic aldehyde, ether, etc. when present in ortho and or para positions to the halogen atom make the later halogen active and replaceable by other group. Electron releasing groups such as amine, hydroxide, OR, R, etc. deactivate the nuclear halogen towards nucleophilic aromatic substitution in the order NH2, then OH, then OR, then R. E. Ullmann reaction. When iodobenzene is heated with finely divided copper at 200 degrees Celsius, diphenyl is formed. This reaction is called Ullmann reaction. Aryl chloride and bromide do not react unless electron withdrawing group like NO2 are present at ortho and or para position to the halogen. Aryl fluorides do not react at all in Ullmann reactions. Fourth, reaction of benzene ring. Aryl halides undergo typical electrophilic substitution reaction, though less rarely than benzene, because halogen have a deactivating influence on the aromatic ring. Next, aryl alkyl halide. Preparation. First, phenyl chloromethane or benzyl chloride is prepared by passing dry chlorine gas into boiling toluene in the presence of light. Second, industrially, it is prepared by chloromethylating benzene with formaldehyde and HCl. Properties of aryl alkyl halide. A. Reaction involving halogenation. First, nucleophilic substitution reaction. Second, Wood's reaction. Reaction of benzene ring. Side chain halogenation derivative undergo usually electrophilic substitution reaction. The new substituent enter at ortho and para position. Side chain halogenation. The nuclear halogenation takes place in cold, dark, and in presence of a halogen carrier. Now we will read alkyl halides. Victor Grignard. He is most noted for devising a new method for creating carbon-carbon bond, that is an addition reaction. First, synthesis of Grignard reagent. An organomagnesium compound is made reacting an organohalide with magnesium metal dissolved in diethyl ether. The resulting compound, named a Grignard reagent, has the general chemical formula RMGX. Second, attack on the carbonyl. A ketone or an aldehyde is added to the solution containing the Grignard reagent. The carbon atom, that is bonded to the magnesium atom, bond to the carbonyl carbon atom by nucleophilic addition with the formation of a new compound, which is an alcohol. The Grignard reaction is an important means of making larger organic compounds from smaller starting materials. By careful selection of the starting materials, a wide variety of compounds can be made by this reaction. For this work, Grignard was awarded the Nobel Prize in Chemistry in 1912, jointly with fellow Frenchman Paul Sabatier. Introduction. Alkyl halides are compounds in which a halogen atom is attached to carbon. They have general formula Rx, where R is the alkyl group and X is the halogen atom. The halogen atom bonded to carbon is the functional group of alkyl halides. Alkyl halides are classified as primary, secondary, or tertiary depending upon whether the halogen atom is attached to a primary, secondary, or a tertiary carbon. Alkyl halides are among the most useful organic compounds. They are frequently used to introduce alkyl group into other molecules. Structure. Let us consider methyl chloride for illustrating the orbital makeup of alkyl halide in methyl chloride. The carbon atom is sp3 hybridized. The chlorine atom has a half-filled p orbital in valence shell. The carbon-chlorine bond is formed by the overlap of an sp3 orbital of carbon and the half-filled p orbital of chlorine atom. Each carbon-hydrogen bond is formed by the overlap of an sp3 orbital of carbon and the s orbital of hydrogen. All bonds are single bonds. The hydrogen-carbon-hydrogen and hydrogen-carbon-chlorine angles are approximately tetrahedral. Nomenclature. Alkyl halides are named in two ways. First, common system. In this system, the alkyl group attached to the halogen atom is named first. This is then followed by an appropriate word: chloride, bromide, or fluoride. Notice that the common name of alkyl halides are two word names. Second, IUPAC system. The IUPAC name of alkyl halides are obtained by using the following rules. First, select the longest carbon chain containing the halogen atom and name the alkyl halides as a derivative of the corresponding hydrocarbon. Number the chain so as to give the carbon carrying the halogen atom the lowest possible number. Indicate the position of the halogen atom by a number and by fluoro, chloro, bromo, or iodo. Name other substituent and indicate their positions by numbers. The examples given below show how these rules are applied. Notice that the IUPAC names of alkyl halides are one-word names. Method of preparation of alkyl halides. Alkyl halides can be prepared by the following methods. First, halogenation of alkanes. Alkanes react with chlorine or bromine in the presence of UV light or at a high temperature, that is 400 degrees Celsius, to give alkyl halide along with polyhalogen derivatives. This method is not used in the laboratory because of the difficulty of separating the products. Second, addition of halogen acid to alkenes. Halogen acids add to alkenes to yield alkyl halides. The mode of addition follows Markovnikov's rule, except for the addition of HBr in the presence of organic peroxides. These are some examples given. Third, action of halogen acids on alcohol. Alcohol react with HBr or Hi to produce alkyl bromides or alkyl iodides. Alkyl chlorides are produced by the action of dry HCl in the presence of zinc chloride catalyst. Fourth, action of phosphorus halides on alcohols. Alcohols react with phosphorus halides to form alkyl halides. Alcohol react with phosphorus halide to give alkyl halide. PBr3 or Pi3 are produced in situation by the addition of bromine and iodine to red phosphorus. Fifth, action of thionyl chloride on alcohols. Alcohol react with thionyl chloride, that is SOCl2, in the presence of pyridine to produce alkyl chlorides. Pyridine absorbs hydrogen chloride as it is formed. Sixth, halogen exchange reaction. This reaction is particularly suitable for preparing alkyl iodides. The alkyl bromide or chloride is heated with a concentrated solution of sodium iodide in acetone. Alkyl fluoride are also prepared by treating an alkyl chloride or bromide with inorganic fluorides. Physical properties of alkyl halides. First, CH3Cl, CH3Br, CH3F, and CH3CH2Cl are gases at room temperature. Other alkyl halides up to C18 are colorless liquid. Those beyond C18 are colorless solids. Second, alkyl halides are insoluble in water but soluble in organic solvent. The insolubility in water is due to their inability to form hydrogen bonds with water. Alkyl bromide and iodides are denser than water. Alkyl chlorides and fluorides are lighter than water. Alkyl halides have higher boiling point than alkanes of comparable molecular weight. For a given halogen atom, the boiling point of alkyl halide increases with the increase in the size of the alkyl group. For a given alkyl group, the boiling point of alkyl halides follow the order Ri, then Rbr, then Rcl, and then Rf. Chemical properties of alkyl halides. Alkyl halides are very reactive compounds. They undergo substitution, elimination, and reduction reactions. Alkyl halides also react with the metal to form organometallic compounds. HSAB, hard and soft acid base principle. According to hard and soft acid base principle of Pearson, hard acids are those species which have less tendency to accept an electron pair, like H positive, Li positive, Mg2 positive, Cr3 positive, Al3 positive, etc. And hard bases are those species which have less tendency to donate electron pair, like F negative, O2 negative, etc. A hard base prefers a hard acid, whereas a soft base prefers a soft acid. Basicity and nucleophilicity. A negatively charged species can function as nucleophile as well as like base, but its nucleophilicity and basicity are different. Nucleophilicity of the species is the ability of the species to attack an electrophilic carbon, while basicity is the ability of the species to remove H positive from an acid. The nucleophilicity is determined by the kinetics of the reaction, which is reflected by its rate constant K, while basicity is determined by the equilibrium constant, which is reflected by its Kd. The order of nucleophilicity of different species depend on the nature of solvent used. For instance, let us make F negative, Cl negative, Br negative, and I negative with their counter cations as Na positive and see their nucleophilicity order in different solvent. There are four categories of solvents, namely non-polar as CCl4, polar protic as H2O, polar aprotic as CH3SOCH3, and weakly polar aprotic CH3COCH3. Polar solvents are able to dissociate the salt, that is, ion pairs can be separated. On the other hand, non-polar and weakly polar solvents are unable to dissociate salt, so they exist as ion pairs. The ion pairing is strong when ions are small and have high charge density. In non-polar and weakly polar aprotic solvent, all the salt will exist as ion parts. The ion pairing will be strongest with the smallest anion and weakest with the largest anion. Thus, the reactivity of halogen decreases with decreasing size. Thus, the nucleophilicity order of halogen in such solvent would be iodine, then bromine, then chlorine, and then fluorine. In polar protic solvent, hydrogen bonding or ion dipole interaction diminishes the reactivity of the anion. Stronger the interaction, lesser is the reactivity of anion. F negative ion will form strong hydrogen bond with polar protic solvent, while weakest ion dipole interaction will be with I negative ion. Thus, the nucleophilicity order of halogen in polar protic solvent would be iodine, then bromine, then chlorine, then fluorine. Polar aprotic solvent have the ability to solvent only cations. Thus, anions are left free. The reactivity of anions is then governed by their negative charge density. Thus, the order of nucleophilicity of halogen in polar aprotic solvents would be fluorine, then chlorine, then bromine, then iodine. On the basis, certain nucleophilicity orders are: first, in polar protic solvent, Hs is greater than Ho. In weakly polar aprotic solvents, CSF, then RBF, then KF, then NAF, then LIF. Bases are better nucleophiles than their conjugate acid. For example, OH negative, then H2O, and NH negative is greater than NH3. In non-polar solvent, CH3 is greater than NH2, greater than OH, greater than F. When nucleophilic and basic sites are same, nucleophilicity parallels basicity. When the atom bonded to nucleophile site also has an unshared pair of electron, nucleophilicity of species increases. Next is nucleophilic substitution reaction. Nucleophilic displacement by SN1 and SN2 mechanism. Here is the mechanism of SN1 and SN2. Stoichiometry, inversion and racemization, only inversion. Molecularity, SN1 is unimolecular, SN2 is bimolecular. Reactivity, in SN1 it is tertiary, then secondary, then primary, then methyl group. In SN2 it is methyl group, then primary, then secondary, then tertiary. Structure of R determining factor, stability of R positive, steric hindrance in R group. Nature of X, Ri, then RBr, then RCl, then RF. Solvent effect on rate. Rate increases in polar. Catalysis, Lewis acid example, Ag positive, AlCl3, ZnCl3. In SN2, none. Competitive reaction, SN1 elimination rearrangement, SN2 elimination. The SN2 reaction. Mechanism and kinetics. The reaction between methyl bromide and hydroxide ion to yield methanol follows second order kinetics. That is, the rate depends upon the concentration of both reactants. The simplest way to account for the kinetics is to assume that reaction requires a collision between a hydroxide ion and a methyl bromide molecule. In its attack, the hydroxide ion stays far away as possible from the bromine. That is, it attacks the molecule from the rear and begins to overlap with the tail of the sp3 hybrid orbital holding bromine. The reaction is believed to take place. In the TS, the carbon is partially bonded to both OH and Br. The COH bond is not completely formed. The CBr bond is not yet completely broken. Hydroxide has a diminished negative charge since it has begun to share its electron with carbon. Bromine has developed a partial negative charge since it has partially removed a pair of electrons from carbon. At the same time, of course, ion dipole bond between hydroxide ion and solvent are being broken, and ion dipole bond between bromide ion and solvent are being formed. Stereochemistry. Both 2-bromooctane and 2-octanol are chiral. The negative bromide and the negative alcohol have similar configuration, that is OH occupy the same relative position in the alcohol and bromine does in the bromide. We see that OH group has not taken the position previously occupied by bromine. The alcohol obtained has a configuration opposite to the bromide. A reaction that yields a product whose configuration is opposite to that of the reactant is said to proceed with inversion of configuration. Reactivity. In SN2 reaction, the order of reactivity of Rx is CH3X, then primary, then secondary, then tertiary. Difference in the rate between two SN2 reactions seem to be chiefly due to steric factors and not due to electronic factors, that is ability to withdraw or release electrons. The SN1 reactions, mechanism and kinetics. The reaction between tert-butyl and hydroxide ion to yield tert-butyl alcohol follows first-order kinetics. That is, the rate depends upon the concentration of only one reactant, tert-butyl bromide. SN1 reaction follows first-order kinetics. Stereochemistry. When 2-bromo-octane is converted into alcohol under conditions where first-order kinetics are followed, partial racemization is observed. The optically active bromide ionizes to form bromide ion and the flat carbocation. The nucleophilic reagent then attaches itself to carbonium ion from either face of the flat ion. If the attack were purely random, we could accept equal amount of two isomers, that is, we would accept only the racemic modification, but the product is not completely racemized, for the inverted product exceeds in enantiomer. Some of the important nucleophilic substitution reaction of alkyl halides are described below. First, reaction with aqueous KOH. Alkyl halides react with aqueous potassium hydroxide to form alcohols. Second, reaction with moist silver oxide. Alkyl halides on treatment with a suspension of silver oxide in moist ether produce alcohol. Halogen atom is substituted by OH group. Third, reaction with sodium alkoxides. Alkyl halides react with sodium alkoxide to form ethers. Sodium alkoxides are prepared by dissolving metallic sodium in excess of the appropriate alcohol. Fourth, reaction with ammonia. When an alkyl halide is heated with an alcoholic solution of ammonia in a sealed tube, alkylation of ammonia takes place. A mixture of different classes of amines result. Fifth, reaction with sodium cyanide. Alkyl halide react with sodium cyanide in a suitable solvent to form alkyl cyanide or nitrile. Halogen atom is replaced by CN group. Sixth, reaction with RCOOAg. When an alkyl halide is heated with an alcoholic solution of the silver salt of a carboxylic acid, an ester is formed. Seventh, reaction with acetaldehydes. Alkyl halide react with sodium acetaldehydes to form higher alkynes. Eighth, reaction with KHH. Alkyl halide react with alcoholic potassium hydrosulfide to form thiols. Halogen atom is substituted by SH group. Next, elimination reaction. Reaction with alcoholic KOH. Alkyl halide react with alcoholic KOH to form alkenes. The reaction involves the elimination of HX from the alkyl halide and is called dehydrohalogenation reaction. Reaction with Mg alkyl halides react with magnesium metal in dry ether to form Grignard reagent. Next, reaction with lithium alkyl halides react with lithium in dry ether to form alkyl lithiums. Next, alkyl lithiums behave in the same way as Grignard reagent but with increased reactivity. Woods reaction. Alkyl halide react with metallic sodium in dry ether to give alkane with the double number of carbon. Nucleophilic substitution in neopentyl halides. Although neopentyl halides is a 1-degree halide, it does not undergo nucleophilic substitution by SN2 mechanism because it is highly sterically crowded to be able to form a transition state. So neopentyl halide has a greater tendency to undergo nucleophilic substitution by SN1 mechanism. Although the initially formed carbocation is a primary carbocation, it rearranges to give a more stable carbocation, which is then attacked by a nucleophile to give corresponding product. So now these are some illustration related to the topic alkyl halides. So thank you.